All right, we're down in our chill water control area of the plant. What we have down here are 4 steam turbine driven chillers. Right behind me you can see that's one of the world's largest chillers that is produced today. You're looking at 8,000 tons of capacity. We use R22 as a refrigerant. That's what allows us to get to that capacity. If we were to switch to R134A, we would actually lose about 3,000 tons of capacity. We have 2 of these chillers in this facility, and then we have 2 other chillers that are half the size, 4,000 tons of capacity, chillers 1 and 2. Again,
tons, Travis, what do you mean by that?
That's ton hours, so that's the amount of load it can produce. If you want equivalent to like a house, your standard household unit's anywhere from 1.5 to 2.5 tons. So you can look at it that one of these small chillers can do, 2,000 homes. So we're heating and cooling the entire campus, 3 hospitals, and when everybody's on site, students, faculty, staff, you're looking at a population anywhere from 60 to 70,000 people that we're heating and cooling centrally from this located plant, as well as the 2 other ones on campus. So right here you're looking at 24,000 tons of cooling capacity, and again, they're all steam turbine driven, using 175 pounds of steam in this facility. Other central plants across campus have a mixture of steam turbine driven and electric, like the cogen facility on the west end of campus is all electric driven chillers at 5,000 tons of capacity for each of the 6 chillers, so 30,000 tons of capacity over there. In our Walnut Street facility, we're looking at about another 24,000 tons or so of cooling at that facility. So plenty of capacity for the entire campus. But we're using on a peak day around 52,000 tons of cooling capacity. So we have lots of redundancy, which is good. Campus has become more efficient over the years. At one point, we thought we were going to have to install quite a few more chillers. It doesn't look like we will unless we switch the Freon at the Charter Street plant from R22 to 134A. Then we're going to lose 25% capacity because there's not a Freon right now that is as efficient for these machines as R22. There's no replacement Freon that we can utilize without dropping load. So we're looking.
Just to recap, like you need to make steam to run the motors that drive these chillers.
Yeah. So as you can see on the one end, we do have a steam turbine driven, which drives the compressor of the chiller, and that compressor is what drives the Freon gas in the Freon cycle here up through the condenser, and it pulls it from the evaporator, the Freon, and it's a continuous cycle, closed loop. And the chill water from campus travels through the evaporator, so the water coming back is about 50 degrees Fahrenheit. When it passes through, the Freon absorbs, picks up the heat, and we control that to about 40 degrees on the chill water supply to campus, and it's a continuous loop. And on the warm, the real hot, humid days, what we call design days, when we have 85-degree wet bulb, the water coming back is about 55, 56 degrees, and we're putting out 40 to 42 degrees of chill water to the campus. The Freon takes the heat from the evaporator, and it transfers it up to the refrigerant condenser, and then on top of the heating plant, you see a big cooling tower, and that's using lake water. And that lake water is pumped through that condenser to absorb that Freon that's carrying that heat. It's actually, absorbing the heat, not the Freon. The Freon's just carrying it. And we take that heat, pump it up to the cooling tower, and then it evaporates in the atmosphere. And that's basically, in a nutshell, the heat in the classroom is being pulled out of that air handling unit and traveling via the chill water back to the chiller, and the chiller uses the Freon to pull the heat out of that water and pump it up to the tower, and the tower actually separates the heat from the water and pumps that heat into the atmosphere. And in a big grand scheme of things, that's how it works.
Kind of like how the campus sweats.
Yep, that's exactly.
And And then what was this neat little efficiency upgrade?
So we did this little experiment here a couple summers ago. You can see this, what we call a little minion, I guess. It's just a ball system. There's little Nerf balls about 5/8 inch in diameter. There's 400 balls in this system right here, in this evaporator. And it's designed so that every 20 minutes when this system is running, when the water is actually passing through the heat exchanger, these balls get pumped through the tubes. Now you got 3,000 tubes in that heat exchanger, and every 20 minutes the 400 balls passes through those tubes and it wipes the tube clean. So any dirt or silt that's in the water does not lay down on that copper tube, and it allows us to be much more efficient. The summer that we tried this experiment out with this company, we saved about $90,000, or actually about $45,000 in costs in energy is how much steam we saved by installing this system. And so the payback on this unit is about 2.5 years. So it was a great project. We were able to use not just the energy data and savings, but we were also able to visually show with some millipore samples how much cleaner the water was in the unit at the end of the year when we took the chiller offline. Plus it saves us labor-wise and safety, because we have to take these lids off every winter and manually punch those tubes, one tube at a time with a long cable and a brush. That if we can get at least 2 or 3 years where we don't have to do that, we save over 2,000 hours of manual labor from having to do that.